Limits involving infinity today. And infinity, I'm going to just admit, is a little bit weird. Infinity is not a number, it's a concept. It's sort of this idea about going on forever. And so when we start thinking about infinity, some things that we know about numbers kind of start to fall apart, and it hurts your brain a little bit when you first start thinking about it. So don't be discouraged if that happens a little bit today. You'll get used to it. So I've got a polynomial graphed here. It's posted on our Moodle page. It wiggles around a little bit in the middle, and then it shoots off the edges of the paper. So we're going to talk about the limits of this graph as x approaches infinity and x approaches negative infinity. So when we say the limit as x goes to infinity of f of x, we're trying to describe what's happening to f of x, or what's happening to the y coordinates as x goes towards infinity. So as we slide out on the x-axis towards infinity, my graph paper only goes to 4, but we'll kind of have to imagine what's going on as x goes to infinity. Now the y coordinates, once you get past 2, seems to be heading downwards rather quickly. So they're kind of on a little bit of a slant. They're not going completely vertical. So they do continue to grow very slowly in the x direction, but they're growing very quickly in the y direction. So as we get out to x equals 50 and 100 and a million, we're going to have y coordinates, but they're going to be really, really far down. So we're going to say as x goes to infinity, the y coordinates are approaching negative infinity. On the other side of my graph, as x goes to negative infinity, so now we're thinking about what's happening to this function as x goes out in the negative infinity direction. Here, the y coordinates are going up off the page, right? So they've got a little bit of a slant to the left, but mostly they're going up. So as x goes to negative infinity, we're going to say y is approaching positive infinity. Let's take a look at a rational function. All right, so this graph is also posted on Moodle. This is a rational function with vertical and horizontal asymptotes. Those asymptotes tell us a lot about infinity as well. So these functions, as x goes to infinity, so as I go towards positive infinity, this graph is not going to infinity, it's kind of settling down. It goes towards that horizontal asymptote. And the whole point of a horizontal asymptote is the graph gets closer and closer, but never actually reaches that y value. So this function, as x goes to infinity, those y coordinates are settling down towards a y coordinate of 1. And eventually, the further out you go, this function will be almost indistinguishable from a horizontal line at y equals 1. So we're going to say that this limit as x goes to infinity is equal to 1. The same thing is actually happening on the left-hand side of this function. There's all kinds of crazy stuff going on in the middle, but a limit at infinity is just saying what's going on the very far left and right-hand side. So as we head out towards negative infinity, what are these y coordinates doing? So as we head out towards negative infinity, these y coordinates are also getting really, really, really close to y equals 1. So this function also has the limit at x goes to negative infinity equal to a positive 1. What about something like the trig functions? Limit as x goes to infinity of sine x. We remember what this function looks like, right? This is, let's see, we're going towards positive infinity, so I'll just draw the right half of it. Sine looks like this, and it keeps doing this wave thing over and over and over again, forever and ever, trapped between positive 1 and negative 1. All right, so this function isn't going towards infinity or negative infinity. It's not shooting off my graph paper in either direction as we go out to the right of the x-axis. And it's not really leveling off like a horizontal asymptote towards a particular number. This graph never, ever, ever makes up its mind to settle down to one y coordinate or to blow up to infinity or negative infinity. So we're just going to say this limit does not exist. And now you've seen all the things that can happen at infinity. You can get an answer of infinity, negative infinity, an actual number, or does not exist. We want to get a little more methodical about calculating these limits as x goes to positive and negative infinity so that we don't have to rely on graphing technology to draw us a good picture to evaluate them. So if we have something like a polynomial like x to the n, so if we have like x cubed or something like this, if x is going to infinity, then x to the n is also going to be going to infinity. So if I let x go to infinity and then I cube it, that's just going to also be going to infinity. It's just going to get to infinity a little bit faster than x would by itself without the exponent. If x is going to negative infinity, we have to pay attention to whether the exponent is even or odd. Okay, so if you've got something negative, so like think of a number like -2, if I raise that to an even exponent, a square, a fourth, or a sixth, that's going to be positive. All right, so if I've got x going to negative infinity, but I'm raising it to an even exponent, that's going to make that negative infinity turn into a positive infinity. But if I've got an odd exponent like -2, we know when we cube a negative number, it's negative. So if you've got negative infinity and you're raising it to an odd exponent, then it's just going to be negative infinity. So these limits at infinity can distribute over addition and subtraction, just like our regular limits. So I could distribute this limit as x goes to negative infinity over the x cubed and over the x. And then we've got limit as x goes to infinity, negative infinity, excuse me, of 1. And we can think about these three limits separately. So on the previous slide, I said if x is going to negative infinity, and we're raising it to an odd power, negative infinity cubed, we can kind of think of it that way, is going to be negative infinity. Same thing with x going to negative infinity. I mean, what's happening to x as x goes to negative infinity? It's going to negative infinity. So this one is also negatively infinite. And then the last one, limit of a constant is a constant, whether x is going to something finite or something infinite. So this limit is just going to be 1. So I've got something going to negative infinity plus more negative infinity plus 1. That's a whole lot of negative infinity. Those two negative infinities are not going to be bothered by the little bitty 1 that we tack on at the end in a positive way. All right, so this limit overall is going to be negative infinity. And you can take a look at the graph of x cubed plus x plus 1, and you'll see as you head out towards negative infinity, the y coordinates are tanking towards negative infinity. This is the first example where things are going to get a little bit weird with infinity. So I have the limit as x goes to infinity of x cubed minus x to the 4th. All right, so the slide I had with the rules on it said that as x goes to infinity, both of these things are going to be headed towards infinity. When it comes to positive infinity, it doesn't matter whether the exponent is even or odd. And I end up with infinity. I'm going to put this in quotes. Infinity is not a number. So we end up with infinity minus infinity. This is going to be one of those indeterminate forms that we talked about. Like we looked at 0 over 0 previously in section 2.3. This is another one of those indeterminate forms. And remember that those happen whenever you have two always rules fighting against each other. So I've got infinity minus something. Usually if that something is a number like infinity minus 5 or even infinity minus 5 million, then the answer is just infinity. The infinity is not bothered about that finite thing being subtracted off of it. So this would be infinite. On the other hand, though, when you're subtracting infinity, so if you have something minus infinity, some regular finite number, 10 minus infinity, 10 billion minus infinity, you're subtracting off an infinite amount of stuff, you're going to end up with something negative, negative infinity. That always happens whenever those numbers are finite. When you've got both of them being infinite, they're fighting with each other. And remember, with indeterminate forms, sometimes the first one wins, sometimes the second one wins, sometimes they come to a happy medium somewhere in the middle at like the square root of 2 or something weird like that. All right, so anytime you get an indeterminate form, you need a trick to be able to evaluate the limit. And the trick for polynomials is going to be factoring. So I'm going to factor, I'm going to say this is the limit as x goes to infinity, and I'm going to factor out the greatest common factor, which is going to be x cubed. And that leaves me with a 1 minus x. And then we know that limits distribute over multiplication. So I can think about these two products separately as x goes to infinity. So x cubed is still headed towards infinity. Then we've got this 1 minus x, right? So that's 1 minus infinity, right? 1 minus something going towards infinity. That's going to be negative infinity. And so we still have infinity and negative infinity, but this time, instead of them being added together, they're being multiplied together. So this is going to be equal to infinity times negative infinity. Okay, so you've got something huge being multiplied by something hugely negative, right? So this is going to be infinite, and that negative sign means it's going to be a negative infinity. So this limit is negative infinity. We've got more indeterminate forms to come in the next video.